Hi everybody, this is lecture 7 and today I'll tell you about cylindrical and spherical coordinates. So I'll start off by doing an example calculation using cylindrical coordinates, then I'll introduce spherical coordinates, make a few points about the conventions that we normally use with them, and then I'll do one or maybe two calculations with spherical coordinates. So all these calculations will be triple integrals. So let's get going, let's get started. The first problem is to compute the volume between two shapes, this sphere, the sphere with the equation you see there, that's the standard sphere, radius 1 about the origin. And the other shape is the cylinder with the equation r equals cosine theta. So I think the first order of business here is to understand this cylinder, this equation. We have more experience working. So most of us have more experience working with Cartesian rather than polar coordinates, or rather than cylindrical coordinates. So I'm going to translate to kick things off. I'll translate this equation for the cylinder, describing the cylinder, to Cartesian coordinates so that we can understand what cylinder we're talking about. So let's do this. So r, in terms of Cartesian coordinates, is root of r x squared plus y squared. And that's equal to cosine theta. So x is r times cosine theta. So cosine theta is x over r. So that's x over root of x squared plus y squared. So that's the equation of the cylinder in Cartesian coordinates. Let's massage this a bit to get it into a familiar shape. So if I multiply both sides by the square root, I get x squared plus y squared equals x. Let me just move x to the other side. Then I get this equation. Now what I'm going to do is add a quarter to both sides of this equation to complete the square, right? If I add a quarter to both sides of this equation, I'm going to get x minus a half squared plus y squared equals 1/4. You see, because if you expand x minus a half squared, you get x squared, and then you get a quarter, which is minus a half squared, and then there is the middle term, which is 2 times x times minus a half. That's minus x. So we had a minus x before, we did not have a quarter, so I added the quarter. Okay, so with this, having written the equation for the cylinder in this way, we can see that we're talking about a circle. The center is the point 1/2, 0, and that the radius squared is a quarter, so the radius is 1/2. So let's draw that circle over here. This is so we're talking about a cylinder in 3D. It goes up, and this cylinder consists of all points x, y, z, where x and y live on the circle with this equation over here. So let's draw that circle. Okay, so the circle will be, so this, as I said, is a circle of radius 1/2, because 1/2 squared is a quarter, and the center is this point 1/2, 0. So it looks like, so this is the center, and here's, you'll draw it a bit bigger. So this is the center of the circle. The whole circle is radius 1/2, so it looks something like this. Okay. Now, so this is in the xy plane. Now, okay, so the cylinder is going to be is a vertical shape. It goes up, and it meets the xy plane on this circle, on this green circle. All right, now let's look at the sphere. So the sphere has radius 1. You can see that here. The radius squared is 1, so the radius is 1 as well. And let's see where the sphere meets the xy plane. It's going to help us draw this, understand the solid region whose volume we're trying to compute. So the sphere meets the xy plane along a circle of radius 1. So here is that circle of radius 1. Okay, so in red is the sphere. So here, so the sphere in 3D. So we're looking at the intersection of the sphere with the plane, with the xy plane, where z is 0. So the original equation of the sphere was x squared plus y squared plus z squared is 1, but on the xy plane z is 0, so I just get the circle of radius 1. So in 3D, our conclusion is that the shape we're looking at is between this red sphere and the green cylinder. The shape looks like this. So we have a sphere, and then we have a cylinder. Oops, maybe I'll draw the outside of the cylinder like this. And the cylinder looks like this. And the region we're interested in is this region here, in between the two. The solid region in between the two. So now let's do this. Let's compute this volume. So the volume is equal to the triple integral over this region of 1 times dv. So let's compute this. So we're going to work over the projection of this solid region onto the xy plane. This is just this disk over here, the disk that's inside the cylinder and on the xy plane. So we'll have bounds. So there's theta, then there's an integral in r, there's an integral in z, and then we integrate 1 times dz, then r dr d theta. Right, because dv in cylindrical is dz r dr d theta or r dr d theta dz. So yeah, the order is we can use whatever order we like. Normally it's useful to have dr d theta in this order. Dz can come before or after r dr d theta. All right, now let's find the bounds. So as I said, the first two integrals, they're describing they're describing a double integral over the projection of our shape onto the xy plane. The projection is this disk over here. Now this disk has equation in green, so this disk has equation r equals cosine theta. So all the angles I need to cover this disk, they go from minus pi over 2 over here all the way to pi over 2 over here, right? And I do have to go all the way to from minus pi over 2. I shouldn't stop at minus pi over 4 because otherwise I will get a secant line. I should have to use the tangent line over here, the angles for the tangent line. So I'm going from minus pi over 2, so theta goes from minus pi over 2 to pi over 2. Now if I fix an intermediate value of theta, and I shoot out a ray with that angle, I will enter the cylinder immediately. I will enter the cylinder when r is equal to 0, and I will leave the cylinder when I will leave this disk when I'm in the boundary circle, when I'm on this circle. But on the circle, I know that r is equal to cosine theta. If I know theta for a point and also know r for that point, using this relation that's true on the circle. So I will leave the circle when r is equal to cosine theta. Now finally, we put in the bounds for z for the innermost integral. So here, what's going on is for each point in the projection of the shape onto the xy plane, we're going to do a vertical integral like this. So if I intersect the solid region, which we're trying over which we're integrating. If we intersect the region of integration with a vertical line, we're going to get a line segment like this, and it's going to the line segment starts and ends in the intersection points with the sphere, and there are 2 intersection points with the sphere. So if I know x and y on the sphere here, so the sphere can be rewritten as x squared. So this is r squared plus z squared equals 1. So there are 2 values of, if I know r, there are 2 possible values for z. One up in the top, z is positive square root of 1 minus r squared. And at the bottom, z is equal to minus the negative square root of 1 minus r squared. So the bounds for the innermost integral go from minus root of 1 minus r squared and all the way to plus the root of 1 minus r squared. Okay, so now that we have all the bounds, we can move on to evaluate. We can move on and evaluate the integral. This integral is a little bit tricky to evaluate, so I figured that I would do this computation in front of you, with you, so we can review some useful integration techniques. So let's do it. So the integral, and so there is an integral in theta from minus pi over 2 to pi over 2. Then there's an integral in r. So we're integrating. Let's see, maybe we can skip ahead a little bit. So the innermost integral is just, so the integral of 1 dz is just z evaluated at the endpoints. If I look at the difference of the values of the endpoints, I just get 2 root of 1 minus r squared. So I'm integrating from 0 to cosine theta 2 root of 1 minus r squared times r dr d theta. Okay, next up, let's observe that the, just a sec. So what's the next step? So the next step is going to be this. I'm going to observe that here we have a square root, so 1 minus r squared to the 1/2, right? The power is 1/2. 1 minus r squared raised to the 1/2, and I can integrate this because 2r, because the derivative of the thing inside the root is minus 2r, and we already have a 2r over here. So let me just say this is integral from. So I'm introducing a minus sign to make this 2r into the derivative of what's inside the square root, and then the integral is 1 minus r squared to the 3/2 divided by 3/2. Then we evaluate this between 0 and cosine theta. Right, let's see what happened here. I'm saying that if I differentiate this, I'm going to get minus this expression. Right, because if I differentiate this thing, the 3/2 drops, cancels with the denominator, and then the 3/2 is replaced by 1/2, which we already have. And then I have to, by the chain rule, I have to differentiate the thing inside. The derivative is minus 2r. So there's that. Here we have 2r. So instead of, because we don't get exactly what we had before, I put a minus sign over here to fix the primitive. Well, now let's evaluate the integral. Let's continue with our evaluation. We're integrating from minus pi over 2 to pi over 2. So 1 minus cosine squared. 1 minus cosine squared theta to the 3/2. Let me just do something here. So there's this denominator, 3/2. I'll just bring it to the front as a 2/3 multiplying. Now, then we have 1 minus cosine squared to the 3/2 minus, and then when r is equal to 0, 1 minus 0 to the 3/2 is just 1. And then d theta. Okay, now let's make a few observations. The thing inside the parenthesis is just sine squared. And then the thing that we have over here, so I'm taking sine squared and raising it to the 3/2. So I'm raising it to the cube power and then taking a square root. So that's the square root of sine to the 6th power, and that's sine cubed. Except that I should observe that I'm taking the positive square root. So the positive square root of sine to the 6th power is the absolute value of sine cubed. Okay. So this absolute value is not really helping us here because absolute values they don't appear in the formulas for primitives and derivatives very often. They do appear in the logarithm. So to get rid of this absolute value, I'm going to make an observation that here the function we're integrating, so absolute value of sine theta cubed minus 1 is an even function. Right? So if I replace theta by minus theta, sine becomes minus sine, but in absolute value. And the absolute value negates, cancels this change, and the function 1 is absolutely does not depend on theta, so if I replace theta by minus theta, 1 does not change. So this function, sine cubed in absolute value minus 1, doesn't depend is symmetric under replacing theta by minus theta. So this is an even function. Here the domain of integration is symmetric around the origin, so I can just say that this whole integral is minus, I can just say it's minus 2 times, so minus 2 times the original thing, but evaluated over half the interval. And then for theta between 0 and pi over 2, sine cubed, sine is non-negative anyway, right? Sine on the upper half of the plane is non-negative, so for angles between 0 and 90 degrees, sine is positive, is non-negative, so we get sine cubed minus 1 d theta. Okay, now next, to integrate sine cubed, here's the trick. If I'm integrating sine cubed, I just observe this is minus 1, is 1 minus cosine. So it's sine squared times sine. Sine squared is 1 minus cosine squared. And then just keep the sine times sine over there. So we can evaluate this. Directly. So integrate the integral with respect to d theta of 1 times sine. So the integral of sine is minus cosine. And then we have minus, or perhaps I should say plus. So next we have we should integrate minus cosine squared times sine. Now here we're taking the square of something, and the derivative of the square, of the thing we're squaring, is just multiplied outside, right? So the derivative of cosine is negative sine. So I can the integral just becomes cosine cubed theta over 3. Because if I differentiate cosine cubed theta over 3, I get 3 times, 3 cancels, cosine squared theta times the derivative of cosine, that's minus sine, which is already over here. Finally, the integral of minus 1 is just minus theta. We'll evaluate this between 0 and pi over 2. Ooh. So this means at this point we can say we made it, but let's get a number. So we get minus 4/3. So cosine of pi over 2 is 0. And so we get another 0 here. right? Cosine cubed is also 0. And then minus pi over 2. And then minus, now we plug in 0 everywhere. So cosine of 0 is 1, plus cosine cubed of 0 is 1 as well. So divide that by 3 minus 0. And if I just check my notes, if we do this, we get 2/3 of pi plus minus 8/9. Okay, so I hope you guys found this this computation helpful, useful. It just serves as a good reminder, a good place. Just felt like a good place to remember how to do some issues that can come up when we're doing integrals and how we can overcome these issues, these problems. Okay, so this is it. This is the second example of an integral with cylindrical coordinates that I wanted to show you. And now I'm ready to, I think we're ready to move on to spherical coordinates. So let's do that. So spherical coordinates. Let's talk about them. So the idea of spherical coordinates is to describe, so these are coordinates for points in 3D. So there are 3 numbers that we associate to points in 3D to describe these points. So positions in 3D. So let's say, let me draw the picture that defines these 3 numbers. So if I have a point, let's say I am looking at a point here in 3 dimensions. I'm going to describe it using, so the original coordinates are here, x, y, and z. I'm going to, instead of using these distances from these planes and using these axes to describe my point, I'm going to describe my point by telling you what is the distance from the origin. And then I'm going to use theta, the angle around the z-axis. So here's, to get theta, let me just do this. So just same theta from cylindrical coordinates. It's the angle of the point around the z-axis. And phi, and the third number I'm going to attach to this point to describe it is phi. This is the angle not around the z-axis, but the angle with the z-axis. So this line over here, this direction that points toward the point, has an angle makes an angle phi with the z-axis, and is rotated by an angle theta around the z-axis, where we measure rotation starting from the x-axis, from the xz plane, rather. Okay, so this is the definition of the coordinates. Let me now relate these new coordinates. Let me write the old coordinates in terms of the new. Let's express x, y, and z in terms of rho, phi, and theta. So x, y, and z in terms of rho, phi, and theta. Okay, so the easiest here is z. So let me show you. So z, so the height of the point is just rho times the cosine, but just by looking at this triangle, z is equal to rho times cosine phi. So let me just write this down. Z is equal to rho cosine phi. And being able to derive these things on the fly rather than remembering them and is really a useful thing. So the trick to deriving these formulas is to start with z. Okay, now to get x and y, so this is going to be a little bit more complicated. To get x and y, so here and here, I'm going to use something that's, I'm going to use r. So r is not really one of the spherical coordinates, but we all know what r is. It's the distance from the z-axis, the distance of the point from the z-axis. So r, and this is not really not part of the coordinates, we'll just say that r is rho times sine phi. Okay, so r is rho times sine phi. Looking at the same triangle, because r is here, so if I multiply rho by sine phi, I get this length over here. Okay, now x, we know from before that x is r times cosine theta by this triangle. So x is rho sine phi, that's r, multiplied by cosine theta. And y is r sine theta, so y is r, here's r written in the new coordinates, and then still in the spherical coordinates, then multiplied by sine of theta. And there you go. These are our formulas for the Cartesian coordinates in terms of the cylindrical coordinate, of the spherical coordinates. Okay, so we can also go back. So for example, rho squared is equal to. I won't go through the other ones because it's going to take a little bit of work. But let me just say, for example, that if I know rho, phi, and theta, I can definitely get x, y, and z. And with some work, if I know x, y, and z, I can also get rho, phi, and theta. For example, rho squared is just equal to x squared plus y squared plus z squared by Pythagoras' theorem twice. Right. So this length squared is equal to this squared plus that squared by Pythagoras. And this is x squared plus y squared by Pythagoras again. So we get this. And with a little bit of work, you can also get formulas for phi and theta in terms of x, y, and z. But I won't dwell on that now. The point I would like to make right now is that it's useful to have some conventions for the angles. So here's some conventions. So first, we're all going to agree that we're only going to think about non-negative rho, right? In theory, you could maybe think that if I have a point in the back over here, I could specify this angle and that angle, and then say you go backwards from the origin. But we're not going to do that. If I want to reach a point at the back, what I'm going to do is increase these angles until I'm pointing in the direction of that point, and then move a rho amount of time in that direction until I get the desired point. So that's the first convention. The other convention is, I think, will be non-controversial, and I'm even willing to negotiate it a little bit. The convention is going to be that theta is between 0 and 2 pi. Right? Okay, so sometimes if you guys prefer to work from minus pi to pi, I'd be fine with that as well. But the important part is that the range for theta should be an interval of length 2 pi. Right, so because this way, if I were in a bigger interval, so this way there's only one point with two possible theta coordinates. Right, so theta is 0 here, but it's also equal to 2 pi here. And so on the x-axis, so points on the x, rather on the xz plane, so these points will, the theta value for them, theta coordinate for them would be ambiguous. It could be 0 or 2 pi, but for all other points, these points will have just a single theta coordinate. And finally, the last convention is that we're going to have phi. So this angle phi over here. I'm just going to. So when phi is 0, I'm in the North Pole, right? Because I'm measuring from the z direction. So if phi is 0, I'm on the z-axis over here. If phi is pi, I'm on the negative z-axis, negative half axis, and in between I'm here on this half plane with angle theta, making angle theta with the around the z-axis. So I'm going to constrain myself to only have phi between these in this half plane. So when phi is varying, changing, I'm moving just inside a half plane. So phi our convention is going to be that phi will go between 0 and pi. So so if I start with this point and change phi backwards, I'm going to move this way, and rightwards I'm going to move this way. So if all possible values, if I touch on all possible values of phi, I'm going to cover a half circle. Now, you guys may be worried, what happens if I want to describe a point in the back of the sphere, on the back of, in the other half of the circle? So how do I describe that point? Well, here's how I'm going to do it. Let me just observe that if rho and phi are fixed but theta is changing, so if I take this point, keep rho and phi fixed but only change theta, I'm going to draw out a circle like this. Now, if instead I had fixed rho and phi but changed rho and theta, sorry, if instead I had varied phi but fixed the other two coordinates, we'll get this half circle. You guys can see that if I want to reach a point at the end of the sphere, what I can do is add. If I want to reach a point in the other half of the circle, what I can do is I add pi to theta, then I get to there, and keep the same phi, and then I'm able to reach a point at the other end. Okay, so this way, so with these conventions, every single point, not every single point, because of the ambiguities for when theta is equal to 0 and 2 pi, and also when rho is 0, all possible angles will still give me just the origin. But let me just say this, that with these conventions, most points in space will just have a single triple of numbers, rho, phi, and theta, describing them. Okay, so that's it. Let's now think about where spherical coordinates will be useful. So spherical coordinates will be useful to describe shapes which are simple, whose equations. Okay, so if I have a shape whose equation becomes simple in terms of rho, phi, and theta, then I probably want to think about, to calculate. If I'm going to do a calculation with a shape that described an equation which is simple in terms of rho, phi, and theta, I probably want to use spherical coordinates to carry out that calculation. So here are some shapes that are with a simple equation. Let's say, here's a simple equation. Take rho and say rho is equal to some number, right? So let's say rho is equal to 1. What shape do I get? So I'm looking at all points with distance 1 from the origin. But phi and theta can be anything. So I'm going to get a sphere, right? So that even justifies a name. So the simplest so a sphere in spherical coordinates just has a very simple equation: rho equal to 1, rho equal to radius, to a constant radius. Okay. Now let's see. What about if I fix theta? If I fix theta, the shape I get, if I vary phi and I vary rho, and fix theta, I'm going to get a half plane. Okay, now if I fix phi, this is an interesting one. If I fix phi, so I fix the angle, but then I let rho go vary as much as it wants, and I'm going to let theta vary as well. The result is that I'm going to get a cone with cone angle phi. So these are shapes that we can describe easily. So cones, half planes, and spheres can be easily described using spherical coordinates. All right, let me now move on to calculations. So I'm going to copy this picture. Before we do the calculation, so let me just paste the picture back. We need the volume element in 3D. So for triple coordinates, for triple integrals in spherical coordinates, the volume element, so dV in spherical coordinates, is rho squared sine phi d rho d phi d theta. Put this in a red box because it's really important. So what I want to do next is quickly convince you that that we need this factor rho squared sine phi over here. So that explain why we have this factor rho squared sine phi. And then I'm going to do a calculation using this, and it's going to give us the expected answer. So I hope that that calculation will serve as some evidence, serve to convince you that this is the correct volume element. Let's first, let me just give you a picture. Let me try to convince you with a picture first. So what I'm going to do is I'm going to look at this point. I'm going to look at this fixed point, and so it has coordinates rho, phi, and theta. And I'm going to vary these coordinates a little bit. So as I vary these coordinates a little bit, I'm going to draw kind of a box in 3D, and it turns out that this box will have volume. Will have a volume that involves this number over here. It won't be delta rho, delta phi, delta theta. It will be that multiplied by this. Okay, let's see that happening. So first, if I start with this point and increase rho by a bit, I'm going to move. So if I move in this direction, if I just increase rho starting from that point, I'm going to get a little segment of size delta rho. Okay, now rho, phi. Next, if I change phi by a bit, if I change phi by a bit, I'm going to move in this direction. So, and this width over, sorry, this length over here. So if I'm moving, if I change phi, I'm still, so the distance from the origin stays rho, but the angle changes. The angle with the z-axis changes. So this is an arc, a small arc in a radius of circle rho. Sorry, in a circle radius rho, and the angle is delta phi. So the increase, so the length. If I move delta phi radians in a circle of radius rho, this length over here is rho times delta phi. Okay, now finally, if I take this point, if I take the point I fixed, and I just increase theta by a little bit, I'm going to move it on this circle by an amount of theta. So this movement is just taking place down here, right? So let me just draw that. If I change the theta angle by adding delta theta to it, I'm going to move on this little segment. So I'm going to move up here like this. And this length, so is r. So if you move delta theta, an angle of delta theta in a circle radius r, this length is, the arc has length r times delta theta. And r in the coordinates, in spherical coordinates, is rho sine phi and multiplied by delta theta. So the conclusion, so this piece over here also has, this piece over here has with rho sine phi delta theta, multiply that by rho delta phi and delta rho, and you get this expression with a bunch of deltas instead of d's. If you make everything an infinitesimal, the deltas become d's. So this is roughly, okay, my picture is not very convincing, I think. Okay, so this little thing that this little piece of, this little volume that I get by just, this little region that I span by just starting with a point and changing the spherical coordinates each by a little bit. So this volume is not the product of the changes in the coordinates, but rather the product of the changes times the scaling factor that we just worked out. Okay, so that's the derivation. I'd like to show you how this works in practice. So here's going to be the example. So the region E is just going to be a sphere of radius 1. No, let's say sphere of radius R. Capital R. Okay, so I'm going to let's compute the volume of this sphere. So that's going to be the triple integral over E 1 times dV. So we know, from if we look at on Wikipedia, the formula, the answer for this volume, the value of the volume of a sphere. So the volume of a sphere of radius r is 4 thirds of pi times r cubed. Let's see this number come out. Of this integral. So let's evaluate the integral by changing to spherical coordinates and using this volume element. Let's do that, and then let's check that the number we get is consistent with the one from Wikipedia. 4 thirds of pi times r cubed. So let's set up this integral. So we're working over a sphere. So we're going to have 3 single integrals times 1 times 1 rho squared sine phi d rho d phi d theta. Okay, so we need to fill in the bounds for this integral. So on a sphere of radius, for a sphere about the origin, a sphere about the origin has points with all possible angles. So it encloses the z-axis. So to cover that whole sphere, I need all possible values of theta. So theta is going from 0 to 2 pi. All right. Now, if and moreover, I also need, even if I fix a value of theta, then the theta slice is going to be a half disk like this of the sphere, right? If I cut my sphere with a half plane with angle theta, the result will be a half disk like this. And to cover this half disk, I need all possible values of rho, or of phi. So phi should go from 0 to pi, from the North Pole to the South Pole. And finally, on a sphere of radius r, the radius. So if I fix phi and I fix theta, and I shoot out a ray with those fixed values, I'm going to enter the sphere immediately when rho is 0. And I'm going to leave the sphere when rho is, well, the radius of the sphere. So now let's evaluate this integral. So we set up the iterated integral. Now it's just a matter of evaluating and checking that we get the correct number. Let me just say that whatever happens in the inner two integrals, the answer for that won't depend on theta. So I can just replace the outermost integral by a factor of 2 pi. Okay. Now there's an integral in phi from 0 to pi. And then there is also so I can also pull out the sine theta, the sine phi. So let me just do that. Yeah, okay, so I hope you guys will agree with this, that I can write this integral as a product of 3 integrals. So the integral in theta is out here, the integral in phi is here, and the integral in rho, with respect to rho, is here. Right, just because, so it turns out that whenever you're integrating a product of 3 functions, and one function of rho, one function of phi, one function of theta, the triple integral of a product of functions is just the product of the integrals of the three functions. Just because the answer, the reasoning is much like what I was doing before. So I was saying, so here, for example, I can pull out sine phi, then I'll be left with the integral of rho squared d rho. That's really a number as far as the other two coordinates are concerned, so I can pull that out of all the integrals. For the other two integrals, a similar thing happens. So I'm just left with the integral with respect to phi sine phi d phi. That doesn't depend on theta, so the integral in theta just gives me a factor of 2 pi, and then I get this. Okay, so now next, what's the integral of, let's compute these two things. So that's 2 pi times, so the integral of sine is minus cosine, evaluated from 0 to pi, and then the integral of rho squared is rho cubed over 3, evaluated between 0 and r, that's r cubed over 3. Now, this here, so cosine of pi is minus 1, so minus minus 1 is plus 1, minus cosine of 0, that's 1, with the minus sign, there's that, so I get 2. So the final answer is 2 times 4 pi, and then divided by 3, so that's 4 pi times r cubed divided by 3. So that's the volume of a sphere, well, the volume bounded by a sphere of radius r. I usually use the word sphere to just mean the shell, the set of points with a fixed radius, rather than with a radius at most a certain value. So if I meant something, let me change that. Let me just be more consistent. So usually you'll just say the ball of radius r. When I mean, so to me a ball is a solid thing, but a sphere is just the surface of the ball. So there you go. So here I should have mentioned that when I did my calculation, I assumed that the ball was centered at the origin. That's fine because volume doesn't depend on the coordinate system, so you can just move, choose a coordinate system that's going to be appropriate for the calculation we're trying to do. Okay, so finally, I would like to do one more calculation. This time, the bounds in spherical coordinates will be a little bit harder. So let's do that. So the last calculation is the volume of a cap of a sphere. Like the North Pole. So volume of the cap of the sphere. So here's the picture. And we're looking at the cap. So that's the North Pole like this. So we're talking about this portion. So it has, it's described by two equations. So we're talking about the region, the solid region that's enclosed by the sphere of radius 1. So our region has radius consists of points with radius at most 1. And the second condition is that it's above the plane where z is equal to 1 over root 2. So our cap, our region, is described by these two inequalities. Rho is at most 1 and z is at least a half. And then we get this shape. Okay. So here's the volume. So let's compute this volume. So it's a triple integral over E of 1 times dV. So E is this red region over here. This red cap. So let's set it up. We're integrating theta from something to something, phi from something to something, rho from something to something, and do 1 times rho squared sine phi d rho d phi d theta. Okay, now so what are the angles? So what angles do we need to theta? So what values of theta do we need to cover this cap? All values. Can you guys see? So this shape it encloses the z-axis, so I need all values of theta to describe it, to cover it. So that's what I'm putting as the outer bound for rho. All values of theta means rho from theta from 0 to 2 pi, or maybe from minus pi to pi. Okay, so next up, to get the inner two integrals, the bounds for the two inner integrals, it's useful to look, like in the previous lecture, to look at the theta slice. So so here's a theta slice. Make it wider. So I'm going to look at a theta slice. So I'm fixing a value of theta between 0 and 2 pi. And then, so fix a value of theta and look at the slice. And what I'm going to get is something like this. So that's what this theta slice looks like. The theta slice doesn't depend, this shape, in this case, it doesn't depend on theta, because the cap is symmetric around the z-axis. So this is the general look of it. So up here, so the equations that we use to describe it are, so up here, rho is equal to 1, and down here, z is equal to 1 over root 2. Okay, so now we're looking at this theta cap, and we have to do an integral over this cap with using these spherical coordinates. So phi in this cap starts up here, where phi is equal to 0, and then it stops at the phi value for this point. All right, so let's see if we can figure that out. So phi starts at 0 up here, and then it stops at this maximum angle over here. Now, what's phi at this point? So I know that so I know that on this point, two things are true. I know that z is rho times cosine phi. I know that z is equal to 1 over root 2, but I also know that at this point, just because this point lives on this line, but I also know that rho is equal to 1 at this point, because this point is on both of these two curves. So on this point, I know that rho is 1. So cosine phi is 1 over root 2. That tells me, I'm sorry for the mess here in my calculation, it tells me that phi is the arc cosine of 1 over root 2, which your calculator will tell you is 45 degrees. That's pi over 4. So the integral in phi goes from 0 to pi over 4. Now finally, we looked at the theta slice, so we fixed theta. Now let's look at an intermediate value of phi between 0 and pi over 4. Shoot out a ray with that angle. So fixed phi, shoot out a ray with that angle. the bounds for rho will be the rho values at these 2 points, at these 2 extreme points. So let me just write back, add here the information that we had last time. So we know this angle here is pi over 4. But phi is some number slightly less, between 0 and pi over 4. Okay, so we know, so the easy bound in this case is the upper bound, right? So I know that it's not so clear when rho enters the region, but it's clear where rho, the last value of rho in this theta slice, this last value is just 1. So I leave the region when I leave the sphere. So rho stops at 1. Okay, so when does rho enter? Well, rho enters on this line, which has equation z equals 1 over root 2. So I'm a little bit unhappy that I didn't plan my notes very well here. But I know that I enter this region when z is equal to 1, z is equal to 1 over root 2. Now z is rho cosine phi. So this tells me that here, rho is 1 over root 2 cosine phi. So I enter the region here, where rho down here is equal to 1 over root 2 times cosine phi. Like this I get from this equation translated to spherical coordinates. And it's perfectly legal to have this phi dependency in the lower bound for the rho integral, for the integral with respect to rho, because rho is the innermost integral. So in fact, these 2 bounds could depend on the other 2 variables, phi and theta. So the phi bound can only depend on theta, the bounds for phi can only depend on theta, and the bounds for theta can only have to be numbers. So that's it. I'm not sure I want to do this integral right now. Yes, and my notes I only set up the integral, so I guess we can call it a day today. Okay, so thank you guys for listening. I hope this information will be enough for you. I hope this information will be enough for you to work on the homework on the subject. But if it isn't, of course, please. I'm here to help. Just shoot me an email or come to office hours. So with that being said, thanks for listening, and we'll see you guys next time.